Hello everyone, welcome you all to the course Unmanned Aerial Vehicle Design, and in today's lecture we're going to see about tilt rotor aerodynamics and tilt wing unmanned aerial vehicles. The tilt rotor and tilt wing configurations represent hybrid convertible rotor, which is a concept designed to provide helicopter-like vertical flight alongside efficient wing-borne cruise. While it is highly capable, these designs are essentially compromises that are less efficient in each specific regime compared to a dedicated helicopter or a high wing loaded fixed wing aircraft. A tilt rotor is a convertible aircraft designed as a compromise to provide the vertical takeoff and hover efficiency of a helicopter combined with the high speed cruise efficiency of a fixed wing aircraft. The aircraft features one or more rotors mounted on the tilting nacelles at the wingtips. Rotors are mounted on the tilting nacelles. These are the tilting nacelles. Right. So, during cruise flight, it will be turning 90 degrees in the forward direction, and for takeoff, it will move 90 degrees upward. So, it is like a limb. Initially, it is like this for hover or takeoff, vertical takeoff, hover or vertical takeoff. Then slowly, once the altitude is gained, this will tilt down to 90 degrees so that it cruises in level flight. The operating regimes of this tilt rotor: the vertical rotors are oriented horizontally, that is, shafts vertical to generate lift like a helicopter, like in this case. Right. These rotors are oriented horizontally, right, like this here, right, and it will generate a lift like an helicopter. And during cruise, that is forward flight, rotors tilt forward 90 degrees to function as propellers, while the fixed wing generates lift aerodynamically. Right. So, it changes from here. Suppose this is the rotor in this case. When it is tilted down here 90 degrees, then this is a propeller in this case. The rotor becomes propeller, and whatever lift is required, it will be generated by the wing on which these propellers are mounted. The aerodynamic principles: hover efficiency versus cruise speed. The primary motivation for the tilt rotor is that helicopters are inherently limited in speed, that is below 170 knots, due to retrating blade stall. By transition to wing-borne lift, tilt rotors can exceed 300 knots, that is approximately 560 km per hour. So, once the rotor from vertical origin, it comes to the forward flight, that is in propeller combination, then the tilt rotors doubles its speed, almost it doubles the speed, it brings to 300 knots. Earlier when it is hovering, it goes up to a speed of 170 knots, but during forward flight, it goes up to 300 knots, which is equivalent to a fixed wing aircraft. Disc loading: the ratio of aircraft weight to rotor disc area is disc loading. W is the aircraft weight and S is representing the rotor disc area. Tilt rotors typically have higher disc loading than conventional helicopters, but much lower than jet VTOLs. VTOLs are vertical takeoff and landings. Power loading: it's a critical parameter determining how efficiency is being judged there. Tilt rotor utilizes wing lift in cruise and which is more efficient than rotor generated lift. It reduces the fuel burn penalty of pure rotary wing flight. The effect of aspect ratio. The side-by-side rotor arrangement in forward flight can behave similarly to a large aspect ratio wing requiring less power to produce lift than a single rotor configuration. In previous class, we have seen single rotor mounted designs, right? So, similar to that, this works. The lift loading ratio, it's a key design metric for hybrid VTOLs, which is the lift loading ratio, which is the ratio between the rotor disc loading and wing loading. We can also call it as S upon W by S. It is the ratio between rotor disc loading and wing loading. For a safe transition, the ratio must be high enough to ensure the slipstream velocity prevents the wing from stalling at the high angles of attack encountered during the conversion phase. Transition phase, the conversion from tilt rotor to propeller for the forward flight, it's a very crucial phase in this kind of configurations, and it is quite challenging. The most critical part of this tilt rotor aerodynamics is the transition between hover and cruise. When it is moving from this position to this position, when it is a rotor here and it's a propeller here, this is the most crucial phase in the tilt rotor flight. The first one is the flow attachment. The aircraft must maintain attached airflow over the wing while the rotors are tilting forward. Transition up, that is hover to cruise, right? So, when it is moving from this vertical to horizontal, when it is coming to forward flight from hover, at that time high air velocity from the rotor slipstream helps in reducing the effective angle of attack of the wing, which in turn delays the stall. High lift devices like Kruger flaps are often required in these kind of configurations. Then transition down, that is cruise to hover, when it again moves back to from forward flight to hovering condition, right? Then it is more difficult because the aircraft is decelerating with lower rotor thrust, which is increasing the wing's angle of attack and the risk of flow separation. So, in either cases, it's quite challenging, but when it goes from cruise to hover, it is bit more challenging. The designer has to be more specifically design it by considering all the aspects like deceleration, right? And because it will have a lower rotor thrust, so the configuration has to be designed based on these parameters. Flight control strategies for tilt rotor mechanisms. So, tilt rotor require a complex flight control system to manage two different sets of control logic. The flight mode, hover, when it is climbing vertically up, then axis of control, the vertical control is controlled using the mechanism of collective pitch, which change on the both rotors. Then we have pitch, that is longitudinal axis. The fore and aft longitudinal cyclic pitch change mechanism is used here. Then in the lateral direction, that is roll, differential collective pitch change helps to obtain this lateral mode. Directional or yawing mode, here differential longitudinal cyclic pitch change control mechanism is been used. It's the same mechanism, but use of mechanism is in a different way. We use collective pitch for roll, longitudinal cyclic pitch change to yaw, fore and aft longitudinal cyclic pitch for longitudinal pitch, and then collective pitch is being used on the both rotors to ensure that it vertically climbs and even comes down, climb up and come down. So it uses the same principle what we have in helicopters, collective pitch and cyclic pitch. During cruise, the longitudinal pitch, we use elevator deflection to control this longitudinal pitch during cruise flight. For speed, we just change the collective pitch change, and directional, that is yawing motion, we use rudder deflection to control this. Flight control system phasing. During transition, the autopilot must progressively phase out hover controls, that is cyclic or collective, and during the phase in fixed wing, the surfaces like elevators, ailerons, rudders, these are in proportion to nacelle tilt angle. The design challenges and penalties which a designer will face in tilt rotor aerodynamics configuration. The very first one is weight penalty, as the tilt rotors carry a significant weight penalty due to the mechanical complexity of tilting nacelles, pivots and heavy actuators, which reduces the payload fraction compared to pure helicopters or fixed wing aircraft. The second challenge is mechanical complexity. Systems must include mechanisms to guarantee both nacelles tilt simultaneously. The propulsion system often require specialized fuel and oil systems which are capable of operating over a 90-degree range. The third one is ground effect. Unlike ducted fans, open rotor tilt rotors benefit significantly from ground effect during takeoff and landing, which increases thrust efficiency when close to the surface. These are some successful unmanned aerial vehicles with tilt rotor mechanism. The first one is Bell Eagle Eye. It's a notable tilt rotor unmanned aerial vehicle developed in the 1990s. It uses rotors at the wingtips to operate like a helicopter for VTOL, but transitions to fixed wing flight for efficient cruising. So once it has taken, it takes off from the runway vertically, this will be deployed 90 degrees in this forward direction, so that in cruise flight it is like a fixed wing aircraft. These rotors in vertical becomes propellers, acts like a propellers when it is in forward flight, and this wing provides a sufficient lift during the cruise flight. This is one more example of tilt rotor aerodynamics, that is Bell V247 Vigilant, and it is also called V280 Valor. The modern developments focusing on high speed, long range unmanned missions, V280 is the basis for the manned version but informs UAV design. So, this is the cruise flight. If it is taking off or landing, it can tilt it back to 90 degrees here, and these propellers in forward flight will act like a rotors. Tilt wing unmanned aerial vehicle. It's a similar concept to tilt rotor mechanism, but there is a slight change here. So that change we'll see in these coming slides. A tilt wing aircraft is a hybrid VTOL, that is vertical takeoff and landing, and this configuration where the entire wing assembly including the engines and rotors, propellers, pivots about a transverse axis on the fuselage. There is a hover mode. The wing is rotated to a vertical position 90 degrees incidence and the propellers function as rotors to provide vertical lift. This is the hover flight and this is the cruise flight. Here the complete wing is from this horizontal axis. If you take, this wing was horizontal earlier and to vertical takeoff and landing it has moved 90 degrees. Complete wing, not just the rotors, the complete wing configuration is been moved to 90 degrees. Once it attains the altitude, again this moves back, this complete wing moves back to this 90 degrees for the forward flight. And then these rotors will act like a propeller, like what we have seen in tilt rotor mechanism. But in tilt rotor mechanism, only the rotors will be moving to 90 degrees up or 90 degrees down, either in the hover flight and in the forward flight. But in case of tilt wing unmanned aerial vehicles or tilt wing vehicles, the entire wing shifts. The entire wing shifts with 90 degrees incidence. Coming to the cruise mode, the wing is rotated to a horizontal position and the propellers provide forward thrust while the wing generates aerodynamic lift. The key distinction here, unlike a tilt rotor where only the nacelles tilt, the tilt wing assembly moves as a single unit, which is intuitively simpler in terms of nacelle attachment and root hinge mechanisms. The aerodynamic principles and efficiency. Tilt wing designs are compromises intended to combine helicopter like hover with efficient wing-borne cruise flight. Cruise efficiency. Tilt wings are generally more efficient in cruise than tilt rotors. Since the wing is aligned with the prop wash in hover, it can attain a higher net lift than configurations where the wing blocks the rotor downwash. Power loading. It is the hybrid systems like tilt wings allow for higher speeds than conventional helicopters, which are limited by retreating blade stall. By utilizing wind generated lift for cruise, they significantly reduce the power required to remain airborne compared to pure rotary flight. The transition phase, which is the conversion phase from cruise flight to vertical takeoff and landing, then again vice versa from vertical flight to forward flight. The most critical and difficult part of the tilt wing flight is the transition between hover and cruise. The first one is wing stall. During transition, the wing is at an extreme angle of attack and tends to stall. This makes controllability difficult unless the wing is almost entirely within the prop wash and the engines maintain high power settings. Flow attachment. To prevent stall, high lift devices like Kruger, leading edge flaps or trailing edge flaps are often employed to maintain attached flow over the wing during the conversion process. Transition down. This is the most dangerous maneuver. As the aircraft decelerates, the rotor thrust is low, reducing the slipstream, velocity over the wing and increasing the risk of flow separation and loss of control. The design parameters and metrics which usually are considered for tilt wing unmanned aerial vehicles is lift loading ratio. It is the ratio between rotor disc loading and wing loading. A high ratio is desired for a safe transition to ensure The slipstream velocity prevents wing stall, but this demands more engine power and a larger, heavier wing, which reduces overall efficiency. Propulsion constraints. Tilting the entire wing engine assembly requires specialized fuel and oil systems capable of operating at least at 90 degrees angular range. The flight control strategies which are used here: tilt wing unmanned aerial vehicles requires complex flight control system to phase in different control modes based on wing tilt angle. The very first one is hover mode. So, if it is vertical, the collective pitch change on the both rotors is to be performed, and if it is for pitch during vertical flight, cyclic pitch or longitudinal thrust vectoring is done to control this pitch, and in order to control the roll, the differential collective pitch is performed. For yawing, tail rotor or differential cyclic pitch is performed. Coming to the cruise flight, in order to obtain control over pitch, elevator is deflected, and for yawing, rudder is deflected, and for obtain rolling, ailerons or differential collective pitch is performed. These are some notable examples of tilt wing unmanned aerial vehicles. The Boeing Vertol VZ2 used cyclic for pitch and differential collective for roll. Right. Here you can see the tilt wing concept, like how the complete wing incidence is changed to 90 degrees. It has been completely moved, and this is the front view of that. And the Chance Wout XC142, which was a tilt wing which demonstrated impressive performance but was ultimately more expensive than equivalent STOL aircraft. STOL is short takeoff and landing. So, this is an example of XC142. This is tilt wing concept. Once the altitude is attained, this will move down to a fixed wing configuration and it cruises, and at the time of landing again it goes back to the 90 degrees in the vertical direction, and then it lands in this way. Here it is landing. So, after it lands, then it will be in the normal position. Again, when it goes for takeoff, it will go for vertical takeoff and landing, and then cruise will be forward flight. This will be turning like this. This will turn for 90 degrees. It will be like a fixed wing aircraft. And in unmanned aerial vehicle applications, Aerovironment, which is a SkyTote, which is a tilt wing body unmanned aerial vehicle utilizing a high aspect ratio wing and tail surfaces. This is tilt wing concept. Skate. Skate is an unmanned aerial vehicle with tilt wing mechanism application. A small UAV with twin electric motors on the leading edge that tilt to allow VTOL and transition to horizontal flight. These are the electric motors. Boeing Eagle Eye, which is often classified as tilt rotor but noted in some text for its use of tilt wing technology for efficient cruise. In this case, even this wing can be moved. The design traits of the tilt wing unmanned aerial vehicles is the complexity. Tilt wing mechanisms are heavy and mechanically complex, leading to reduced payload fraction compared to dedicated helicopters or fixed wing unmanned aerial vehicles. Cost. The acquisition and operation costs are typically higher than conventional aircraft due to the dual regime requirements. Tactical advantage. Despite the penalties, tilt wings are superior for missions requiring both high-speed transit and battlefield mobility without the need for launch and recovery infrastructure. Conclusion of today's lecture. The fundamental trade-off. Tilt rotor and tilt wing systems are master classes in aerospace compromise. They successfully bridge the operational gap between helicopters and fixed wing aircraft, offering the unique capability of VTOL and high-speed cruise in a single airframe. The price of versatility. This comes at a significant cost. Both configurations incur a substantial weight and complexity penalty due to the tilting mechanisms, actuators, and specialized systems. This directly reduces the payload fraction and increases acquisition and maintenance cost compared to conventional aircraft. While both configurations solve the same problem, they do so with different aerodynamic philosophies. Tilt rotor prioritize a simpler wing structure and leverage rotor slipstream for wing-borne flight, but faces complex nacelle design. Tilt wings offer potentially higher cruise efficiency by aligning the wing with airflow, but introduce a more severe transition challenge due to the extreme angles of attack of the entire wing. The aerodynamic bottleneck, which is the defining challenge for both configurations, is the transition phase. Maintaining attached airflow and controlled flight while converting between rotor-borne and wing-borne lift requires precise management of lift loading ratio and often necessitates high lift devices like Kruger flaps to prevent stall. The control lock complexity. The transition is managed by sophisticated flight control systems which must seamlessly phase control inputs, gradually replacing hover controls, which is cyclic and collective pitch, and with fixed wing surfaces like elevators, ailerons in proportion to nacelle or wing tilt angle. Tilt rotor and tilt wing unmanned aerial vehicles represent the pinnacle of multi-mission design, and their complexity is justified for missions demanding both the flexibility of vertical lift and speed and range of fixed wing flight, making them invaluable for modern aerospace applications despite their inherent design penalties. These are the references used for this lecture. Thank you.